All right. So welcome to Math 331 problem solving. Today is Yankee Elimination Day, so there will be munchkins to celebrate that. Yes. Yes, I was about to say there's a support line. I have had issues with that, but anyways. Several of you have been wondering about homework. What I decided to do is, since we've been thrown a little bit off schedule with all the perspectives visiting, and too many of you have not seen a proof of the fundamental theorem of calculus, let's prove the fundamental theorem of calculus today. There will be no homework due on Friday, and we'll just shift everything back.
Best prof ever.
Yeah. Right. But what fundamental theorems do you know? Okay? Fundamental theorem of calculus, fundamental theorem of arithmetic. Numbers have unique factorizations, at least if you write the primes in increasing order.
Isn't there one for algebra?
There's the fundamental theorem of algebra in terms of a polynomial degree n has n roots. Yes. That is considered a fundamental theorem. The linear algebra 1 is not. It is putting on airs and pretense. Okay? How many of you have seen a proof of the fundamental theorem of calculus? Okay.
I really like that.
Was it rigorous?
Probably not.
How many of you are math majors? Wow, I should have asked this question earlier in the semester. How many of you are potential math majors? I was going to say, because I realize we have some sophomores. How many of you are at least a major in a science or math? I'll throw in economics if necessary.
Is computer science?
Yes, computer science counts. All right. Alright. This is something you should know, okay? You do not get the label fundamental lightly. You either have to earn it or you have to know someone. Right? Yeah. Well, that's the only way I can explain the linear algebra part. It's who's writing the books. This is something you should know. So typically, we will say f is the antiderivative of little f if the derivative of big F is little f. So you call this the antiderivative, you'll call it the integral, or the indefinite integral, something like that. It is not unique which function is the antiderivative. It's unique up to a constant. And that's a nice exercise to prove that it's unique up to a constant. And the content of the fundamental theorem of calculus is the integral from a to b of f of x dx equals f of b minus f of a. But if you just leave it like this is not the fundamental theorem of calculus, this would be the fundamental definition of calculus. This is one of the things that can really upset me, is if you write this without mentioning a specific word. What word must you mention somewhere when you write this? So what does this represent on the left-hand side? If you don't tell me what it represents, I get upset. It's almost as bad as yelling out, "Go Yankees," although on a day like today, what does this represent on the left? The area. If you do not say area, you're essentially defining the symbol. So the reason there's content to the theorem is if this is A, and this is B, and this is the curve y equals f of x, then this symbol is the area under the curve. And if the curve dips below the x-axis, we count it as negative area. But unless you say area, there is no content. Okay? So just make sure you include content. All right. How many of you have taken a real analysis class? Okay. If you have taken a real analysis class, you can then avoid an assumption I'm going to make. I will make the assumption to make the proof a little bit easier. You can cover almost every function that you would need to study with this assumption, so it's a fine assumption to make. I want f to be bounded on an interval ab. My interval will always be finite. And then if it's finite, I don't have to worry about infinities. And I will also want f prime to be, I'll say, continuously differentiable on ab. As you go further and further in mathematics, you start trying to impress your friends with what's the weakest assumptions you need to prove something. Okay? And then when you start doing mathematics, you realize oh, well, my function's always infinitely differentiable, so I'm going to just use that and move on. So you do not need f prime to exist. You do not need f prime to be differentiable. But if I assume f prime is differentiable, then it makes the argument a lot easier. I don't have to appeal to uniform continuity. I can actually just use results from the mean value theorem. How many of you remember the mean value theorem? Okay, we will also include a little bit on the mean value theorem today. It's a great theorem. It's really worth knowing. So here's a nice fact. If f prime is continuous on AB, then f is bounded on AB. And by bounded, I mean the following. There exists a C such that for all x in the interval, we have the absolute value of f of x is less than or equal to C. Instead of using the letter C, what might be a better letter to use? C is fine, but maybe B for bounded. Doesn't really matter. I've already used B. I've used a little b, but yeah. So this is a nice result, that if our function is differentiable on a nice interval, then it's going to be bounded. So a lot of the functions you've studied are actually bounded. So for example, let's try looking at one or two functions. Let's try f of x equals 3 to the 2x plus 19 cosine x squared minus x plus, let's do minus 8x to the 4th. And let's say the interval AB is the interval 2, 4. I'm not even going to try to do things well. I just need something to be bounded. So remember how we did some games earlier and we proved that a game had a winning strategy without necessarily being able to prove what it was? It's an existence argument. For a lot of what we're doing, we just need that a bound exists. We do not need the optimal bound. Now, what would we gain from the optimal bound? We would have some idea of how quickly things settle down. We'd have some idea on convergence. But if I just want to prove the fundamental theorem of calculus, I just need the existence of a bound. So I am going to argue really bad. I'm going to use the triangle inequality. The absolute value of some difference is less than or equal to the sum of the absolute values. So this will be less than or equal to 3 to the 2x plus 19 cosine x squared minus x plus 8x to the 4th. This is extremely wasteful because this quantity is clearly going to be negative. This quantity here is clearly going to be positive. So maybe if this is large, I might want x to be closer to 2 to make this whole expression large. But I just need there to be some bound. So when x is between 2 and 4, how large is 3 to the 2x? It's at most 3 to the 8. What about 19 cosine x squared minus x? What's the largest value that takes on for x between 2 and 4? Yeah, 19. Don't even bother trying to figure out what the best value is. And 8x to the 4th, what's the largest that will be? I'm sorry? So how large could 8x to the 4th be on the interval 2, 4? Math. You can do it without multiplying. It's 8 times 4 to the 4.
Yeah.
And this would be less than or equal to 100 to the 100. I mean, I'm pretty safe if I write something like that. Right? So the first question is, how do we go from knowing that the function is differentiable to know that the function is bounded? How does this help us? So the first thing we're going to use is the mean value theorem. So this will help you if you continue on to real analysis. So mean value. How many of you have ever seen the TV show Friends? Every episode of Friends but the first and the last has something in common. What is that thing? in terms of the titles of the episodes?
Oh, the one.
The one with.
Yeah.
Every one, but I think the first and the last week is the one with. When I give this lecture, this is the one with the mean value theorem. If at any point in the day you are unsure what you should do next, if you just guess the mean value theorem, odds are you will be right. It is a terrific theorem. How many of you have seen Taylor series? Taylor series are in some sense just a better version of the mean value theorem. The mean value theorem is just giving you the first term, giving you the straight line approximation. Taylor series allows you to go a little bit further. So the mean value theorem says, assume f is differentiable on AB. There exists a C in the interval AB such that f prime of C is f of B minus f of A over B minus A. Or f of B minus f of A is f prime of C times B minus A, or f of B is f of A plus f prime of C times B minus A. So graphically, if this is A and this is B, the line connecting them, the slope of this line is your average speed. And what it's telling you is there must be at least one point in time when your instantaneous speed is your average speed. And these are three different ways of writing it. So this is my instantaneous speed at C is equal to my average speed. This is how far I've traveled is my average speed times elapsed time. And this is where I am at time B is where I started plus my instantaneous speed at some nice time. So for Taylor series, we would just replace C with A. One of the problems with the mean value theorem is that we unfortunately do not have an explicit way of figuring out where that point C is. It's just an existence. That's all right. For a lot of things, that's fine. And what we're going to do is we're going to just use this for some consequences. How many of you have seen a proof of the mean value theorem? How many of you could prove it right now? All right. Anybody know what ingredient goes into the proof of the mean value theorem? And no, do not say the mean value theorem. So there's two theorems that are often said together in calculus classes along these lines. There's the mean value theorem and there's the intermediate value theorem. If f is continuous and f of A is less than C is less than f of B, then there exists a C such that f of little c is big C. And of course you could also have, f of A greater than C greater than f of B. It doesn't really matter. So the way to interpret this is, let's say at A I know I'm here, and at B I know I'm here. So here is f of A, here is f of B. Then no matter what value you choose between f of A and f of B, you must hit it at least once between the interval AB. You might hit it multiple times. So here it looks like we'd hit it 3 times. You might actually hit values that are above f of B. You might actually hit values that are below f of A. But any value in between you must prove. You must hit. If the function were not continuous, then of course this wouldn't be true. If it wasn't continuous, you could have something that goes like this. So you clearly need continuity. Whenever you do something like this, you always want to get a sense of how harsh is the assumption, how restrictive is the assumption. I do not need to assume for the fundamental theorem of calculus that f prime exists. I don't need to assume that it's continuous. It's just a convenience. Here I need continuity. If continuity is gone, it's false. All right, so the question is always, how rigorously do you want to prove this? My answer is not much. All right, this is one of the no-shit theorems. Okay, you start off 20 miles from home. You end up 50 miles from home. At some point, you were 30 miles from home. It's essentially what it means to be continuous. You can make it rigorous by choosing sequences of points and doing partitions. Take the middle point and see, is it equal to 30? If not, is it above 30 or below 30? And then you split your interval in half, and you can keep going like this, get a convergent subsequence. Does this sound familiar?
Yeah, binary search.
Yeah, a binary search. Divide and conquer, right? So if you wanted to make this rigorous, you can. Are people happy enough with this seems reasonable? Then the question becomes, how do you prove the mean value theorem? Well, the mean value theorem, let's think about what's going on. There's a lot of different ways you can do the algebra, but imagine you start off going at 10 miles per hour and end up at 50 miles per hour. At some point, you must have been going 30 miles per hour. That's just the intermediate value theorem. So the question is, how can we apply it here? How can we look at this and say that at some point in time, we must be traveling the average speed? Well, what would happen if we were always traveling faster than the average speed? Let's say our average speed is 30 miles per hour, and we're always traveling greater than 30 miles per hour. What would our average speed be? Greater. What if we're always traveling below the average speed? So we know that for the mean value theorem, as long as we have one point where we're traveling above the average speed and one point where we're traveling below the average speed, by the intermediate value theorem, there must be a point where we're traveling the average speed. So there's a lot of ways people try to prove the mean value theorem. One typical way is Rolle's theorem. What's funny is he was not a supporter of calculus, and now he's known for calculus theorem. There were a lot of people who were concerned about, is calculus rigorous enough? So Rolle's theorem is assume f of a equals f of b equals 0. Then there must be at least one point c such that f prime of c equals 0. This is just the special case of the mean value theorem. And so if you wanted to prove this, how could you prove this? Well, you have several possibilities. Let's assume the first derivative is not 0 at a or b. If it was 0 at both a and b, you're done. If the first derivative is positive at a and negative at b, you're done. So the only way you'd be in trouble is, let's say, both endpoints, the derivative is pointing in the same direction. Well, wait, if the derivative is positive here, then I must have been coming at it from below. So that means my function must have been negative. If my function is positive here, I'm going up. If I'm negative, then at some point I must go down, right? So then I would know that there has to be at least one point where my first derivative becomes negative. And then I can use the intermediate value theorem. So this is the proof by arrows of the mean value theorem. You can make this more rigorous. I'm just trying to give you a sense. How do you get the mean value theorem in general from this? You basically use a key idea from linear algebra. So, do you guys remember your equations of ellipses? X over a squared plus y over b squared is 1. Remember the conic sections? All right. What if I decide to give you an ellipse that's not centered along the chorded axes? Do you remember how to get the equations for this? You just basically lean back. So if you lean and you make this your new coordinate system, then in UV space, it's the equation of a standard ellipse. And then you just rotate your xy coordinates through theta radians. And you basically can write this down with matrices. You can do a change of base formula. This is essentially the whole idea of linear algebra. Boiled down to one picture. Choose a good coordinate system for whatever problem you're looking at. And if this is your system, then you want your coordinate axes to align with the axes of the ellipse. For the most part, I think Boston is better than New York in almost everything. We've seen a recent example in terms of baseball. There is one thing that New York does, or at least a part of New York does, that's better than Boston. Yes.
Streets, like
Yes.
Yeah.
Which part of New York City? It's Manhattan. So Manhattan in New York City is in a really nice grid pattern. Makes it very easy to get around. That's a terrific coordinate system. In Boston, you can actually have, you do have cities like this. I think it's Beacon and Boylston that will cross each other.
Oh, yeah.
As to which one is on top of the other. It makes navigating far more interesting geometrically. Okay? But linear algebra is all about choosing the right coordinate system. And here, this is the better coordinate system. How does this help us? Well, it helps us with the mean value theorem as follows. So here is the general case of the mean value theorem. So here is A, here's B. I basically want to choose new coordinate axes like this. So I'm going to come up with a new function. I want a function g that's going to be 0 at A and 0 at B. So g of A should be it's got to somehow be related to f of x. So g of x is going to be f of x, and then I've got to subtract off something. So I'll subtract off f of a. But now when I put in b, I also want it to be 0. So then this is going to be f of b minus f of a. So let me subtract off f of b minus f of a. But I only want that to happen when x equals b. So I'll multiply this by x minus b and divide by b minus a. And if you look at this new function now, when is this what I want? Or do I want b minus? No, I'm sorry. I don't want x minus b. I think I want x minus a. I want x minus a. And now when x equals a, this part vanishes. And I just get f of a minus f of a is 0. And now when I take x equals b, I'll get b minus a over b minus a, which cancels. That's 1. F of b minus f of a, f of b minus f of a. So now we have g of a equals g of b equals 0. There exists a c such that g prime of c equals 0. And now you go from g prime of c equals 0 to get, we have f prime of c minus f of b minus f of a over b minus a times 1. So I'll leave the rest of the algebra for you. Now that you know the mean value theorem for g, you essentially get it for free for f. This is a common theme. This is a class in problem solving. You reduce something complicated to a simpler case. I want to argue that it's enough to consider the case where f of a, f of b equals 0. That's basically just leaning back. It shouldn't be a big deal to lean back. The question is, what's the right function to subtract off? Well, I wanted to have good behavior at A. I want to have good behavior at B. So I first start off by subtracting f of a to make things nice at A. Now I want to make things nice at B without disturbing what I did to A. And that's why I have this factor like this. So this is a common idea of taking a simple case and then exploiting it. All right, so we now have the mean value theorem. Now we want to see how the mean value theorem implies that the function is bounded. All right, so assume prime is continuous on AB. Okay? So here is A, here's B, here's part of my function. I want to show that my function is bounded. I have to show that my function can't get too large. Well, take any x, and then we know f of x minus f of a over x minus a is equal to f prime of c for some c. Right? So from this we can get f of x is f of a plus f prime of c times x minus a. So if we assume the first derivative is bounded, then our function f is also bounded. because then we know f of x is going to be the most absolute value of f of a plus the maximum value here. So again, I could assume my original function f is bounded. I could assume f prime is bounded. It's a question of what's going to be useful later on. But we've just seen if f prime is bounded, then f is bounded. So the whole idea is we don't want things to be getting too large. Okay? It seems to make sense. If your first derivative is bounded, then your instantaneous speed is never above a certain amount. So your function can't get too large too quickly. All right. So now we should have enough tools to prove the fundamental theorem of calculus. So this is a major result. All right. So what we want to do now is we want to sketch the proof. How many of you remember partitions? That you want to partition the interval? There's a couple of ways of doing the partitions. So sometimes people do what's called a refinement, where you start off with a partition, here's 0, 1, and you partition 1, you get 1/2, and you partition and you get 1/4, and 3/4, and you keep going. So at every step, you split every interval in two. Other people will do, here's 0, 1, then here's maybe 0, 1/2, 1, and then here's 0, 1/3, 2/3, 1. And the next one you would do with quarters. And when you do it like this, each piece is not a refinement of something above. It makes the math a little bit easier if at every point you always split in half. When you do this, your lower sum will always be non-decreasing, and your upper sum will always be non-increasing. When you flip something like this, you can flip which are in your upper and your lower sums. So I will always be splitting with powers of 2. It just makes things a little bit easier. You can, of course, develop the theory for either case. But I wanted to try to highlight to you why you might do something. At the end of the day, we don't care about doing partitions. We care about getting the fundamental theorem of calculus. And so to get the fundamental theorem of calculus at the end of the day, well, it's okay if we are doing just powers of 2, because we don't care about that. So the big idea here is remember what your goal is. And given that our goal is just to get to the fundamental theorem of calculus, we don't need to do a general partition. Okay. So here's how it's going to go. 0, 1 over n, 2 over n, k over n, k plus 1 over n, all the way down to 1. And that'll be n over n. So I'm going to assume without loss of generality that my interval is 0, 1. If it's not, you just put in a's and b's everywhere. Let's keep the algebra a little simple. So I have a function like this, and on each interval, I'm going to find where's my function largest and where's my function smallest. Okay? And that will lead to the upper sum and the lower sum. Is this at least sounding familiar to everybody? Upper sums and lower sums? Somewhat? All right. So there's a beautiful result in real analysis that says if you have a continuous function on a closed bounded interval, it attains its maximum and minimum. That there will be a place where it's largest, there will be a place where it's smallest. So if you want, I may be subtly assuming that right now to just make things work. Let's blow up this interval. So here is k over n, we'll call that xk. Here is k plus 1 over n, we'll call that xk plus 1. And let's say my function looks like this. Then what I do is I approximate it and say, look, the area under this curve, I can take the largest value, I'll do it this way. I'll take the largest value here, and I'll call that uk for my upper sum, and I'll take the smallest value here, and I'll call that lk for the lower sum. And so the true area under the curve is greater or equal to the area from the lower sum, and less than or equal to the area with the upper sum. So we get f of Lk times 1 over n, because that's the distance, is going to be less than or equal to the area of the kth piece, is going to be less than or equal to f of uk times 1 over n. Everybody okay with this? Now we just sum over k. So if we sum k goes from 0 to n minus 1 of f of Lk 1 over n, that's going to be less than or equal to the area, and it's going to be less than or equal to the sum k goes from 0 to n minus 1 of f of uk 1 over n. And we call this piece the lower sum, and in a shocker we call the other piece the upper sum. Okay? And the hope is that as we take a finer and finer partition, that the lower and the upper sums will converge to a common value, and that common value has to be the area. So the first question is, do the upper and the lower sums converge? If we always have each partition is cutting in half the previous, then the lower sums will never be getting smaller, and the upper sums will never be getting larger. You don't need to do that, but it just makes the analysis a little bit nicer. So the first thing is, let's look and see how close are the upper sums to the lower sums. So let's look at un minus ln. Clearly it's non-negative. The upper sum always beats the lower sum, right? Let's hope that this goes to 0 as n goes to infinity. If it doesn't, then boy, is this a bad lecture, right? This is equal to the sum k goes from 0 to n of f uk minus f lk divided by n. Okay? Everybody agree that I've just combined things algebraically? And I can even pull the n outside. It's 1 over n, the sum k goes from 0 to n minus 1 of f uk minus f of lk. Now when you look at this, this is good. I'm on a very small interval, so this should be very small. Unfortunately, I'm summing it n times, so even though it's small, I could make it large because I'm summing it by n. But then I divide by n, so maybe that's enough to keep it small. So we need to show that this is pretty small. Any thoughts on what we could use to analyze f of uk minus f of lk? What could we use? You all know the answer. Yes, right? When in doubt today, use the mean value theorem. Given that there's doubt, you should be using the mean value theorem. Why do we like the mean value theorem? It allows us to talk about differences between points that are close. This is equal to 1 over n, sum k goes from 0 to n minus 1, and then there'll be some set of points ck in those intervals. And then I have to multiply by uk minus lk. Well, how large can uk minus lk be? 1 over n. So this whole thing is going to be less than equal to 1 over n, the sum k goes from 0 to n minus 1, the absolute value of f prime of ck times 1 over n. And now, if we use the fact that f prime is bounded, so this is where we need to use the boundedness of f prime. You can bypass this with real analysis, but if we assume f prime is bounded, then I've got a 1 over n, I have an n from the sum, I have a b from the bound, and I have another 1 over m. So this is going to be less than equal to 1 over n times b times 1 over n, which is equal to b over n, which goes to 0. So here, we assume f prime of x is less than equal to b. So what we've now shown is the upper and the lower sums converge to a common value. We don't yet know how to evaluate it nicely, but we at least know that the upper and the lower sums converge to a common value. Okay. Any questions on this? I am watching the clock to make sure we finish this in one day. All right? We are halfway there. What do you think we should do now? What should we do now? Who's brave enough to say it? What should we do? What should we use? Mean value theorem, of course. The difficulty is, how should we use the mean value theorem? Right? We use the mean value theorem applied to the function little f. What other function might we want to apply the mean value theorem to? You have two choices. One is right, one is wrong. The antiderivative. Right? We want the antiderivative to come into the problem at some point. Right? The goal is to show that the upper and the lower sums are converging to the antiderivative at b minus the antiderivative at a. At some point, the antiderivative should appear. Let's apply the mean value theorem to the antiderivative. So we know this is all true now. We will erase this. Okay. Question? Or? Okay. So I will keep all this stuff over here. So now, so if I look at big F of xk plus 1 minus big F of xk, what does this equal? So what must this equal? So what theorem am I using? So what now has to come over here?
F prime.
Be more specific. Big F prime or little f prime?
Big.
Big F prime at some point, let's call it ck, times xk plus 1 minus xk. Or another way of saying this is f of xk plus 1 minus f of xk is equal to little f at ck times 1 over n. Now, how does that compare to the area of k and our lower estimate and our upper estimate? So I can view this as an area. This is a length, and this is a width. Over here, I'm trying to get back on the screen. So when I come over here, I've got my true area for box k is between the lower value times 1 over n and the upper value times 1 over n. If I take any value of the function, you know it's going to be greater than f of lk, greater than equal to k, and it's going to be less than equal to f of uk. Right? So we know as long as we take any point, it's going to be sandwiched in between. So we know f of lk is less equal to f of ck is less equal to f of uk. If I multiply everything by 1 over n, it's still true. So when I sum this, this is going to be between the lowest sum and the upper sum. So we get L of n is less equal to the sum k goes from 0 to n minus 1 of f of ck 1 over n is less equal to the upper sum. And we know the upper and the lower sums converge to a common value. Right? Because their difference goes to 0. Well, this sum is damn easy to evaluate. If you look at it, what do we have? When we first put in k equals 0, we get f of x1 minus f of x0. Then we add in f of x2 and subtract f of x1. Then we add f of x3 and subtract f of x2. All the way down to the last one, f of xn minus f of xn minus 1. the x1s cancel, the x2s cancel, everything cancels but f of xn minus f of x naught. So we are left with L of n is less than equal to f of xn, which is 1, minus f of x0, which is 0, is less than equal to un. But as n goes to infinity, we know that the upper and the lower sums converge to the true area. And what's nice is the thing that's sandwiched in between. Does this depend on n at all? No. So this has to equal the true area. We've got 6 minutes in the bank. This is the proof of the fundamental theorem of calculus. So we used the mean value theorem twice. We used it once on little f, once on big F. We got a telescoping sum. The idea was we had a partition, and we had what was going on each one of them, and then we sandwiched what we wanted between two things that we could control. All right, so let's do some checks of the fundamental theorem of calculus here. We've got 6 minutes left, and it will allow us to use some of the stuff we've done by induction. So whenever you get a theorem, or if you're trying to prove a theorem, it's nice to do some simple cases and check. So let's check the fundamental theorem of calculus. So I need a really easy function to look at. Constant, thank you. And I'm very grateful you did not say the function that's identically 0. So let's take f of x equals c. Well, if we go from a to b, well, let's always do 0, 1. And here's the function is c. Well, this is just a rectangle. The area is just 1 times c, which is c. What, give me a good function that's the antiderivative of c. What function has derivative little c? Cx. And then we get f of 1 minus f of 0 is c. And this proves the fundamental theorem of calculus is at least correct if we have the constant function. Not a major achievement. We could have done this already. Next function to check. A little bit harder than c. What should we try next? Yeah, to make things a little bit easier, I'm going to just do x. And now, what's the antiderivative going to be if I do x? It's going to be 1/2 x squared. And now the area should be f of 1 minus f of 0 should just be 1/2. Well, if you look at what's going on, here's 0, here's 1. Here's the function f of x equals x. This is just a right triangle. The area is 1/2 times 1 times 1. It still works. And you could have done this for more general, Cx going from A to B. Right. This is so far not that impressive. We're calculating areas of triangles and areas of rectangles. You do not need the fundamental theorem of calculus for this. What should we do now? Now things are getting interesting. And what's the antiderivative of x squared? 1/3 x cubed. And so now we'll get that the area is 1/3. Okay. So this is going to require you, here's 0, here's 1, here's a parabola. You now need to know what the area under the parabola is. Good. That is probably not something that you know. So here's xk, here's xk plus 1. So this is actually going to be the lower value, and this is going to be the upper value. So it's not going to be that hard to calculate the lower and the upper sums. In the interest of time, I will just calculate the lower sum. I actually don't have to calculate the upper sum because they converge to a common value. And so if I can do the lower sum, I can clearly do the upper sum. So the lower sum is going to be the sum k goes from xk. So it's just f of the point k over n times 1 over n. So this is now going to be a sum. K goes from 0 to n minus 1. So I have x squared, so I'm going to get a k squared over n cubed. So it's a 1 over n cubed. The sum, k goes from 0 to n minus 1 of k squared. All right, who remembers the formula for the sum of squares? Yes.
Is it n times n plus 1 times 2n plus 1 over 6?
Yes. Now we have to be careful because we're summing up to n minus 1.
Oh, yeah.
So we will have n minus 1 times n times 2n minus 1, I think plus 1, divided by 6. All that's going to matter, though, is the leading term. I don't care about the n squared term up here because I'm going to divide by n cubed. So the main term is n times 2n over 6. That's 1/3 n cubed. So the main term is going to be 1/3 plus something of size 1 over n. And that does match what we have. So that now proves the fundamental theorem of calculus is consistent with the function x squared. If you want to do x cubed or x to the 4th, any of that stuff, we can now do that because we know how to use induction and find formulas for these power sums. This is one of the reasons why we actually care about finding formulas for the power sums. In a good calculus class, you should be using that to build intuition and confirming that the fundamental theorem of calculus is reasonable. When you have something, it's nice to be able to check the answer. One of my students saved his company millions of dollars. Something just didn't look right. And he just did some quick calculation, and then eventually found, somebody put a minus sign somewhere by mistake. And it was significantly changing the financial investment policy the company should have been pursuing. You always want to look at something and say, is this reasonable? If you can check things for more and more cases, you start to build up confidence. All right, this is a good place to stop. So